Hello everyone, welcome to my talk about Unary prime languages. This is a joint work with Orna Kupferman and Nicola Mazzocchi, published at MFCS 2020. Compositionality is a very important notion in computer science that allows to make some complicated problems easier. The idea is as follows. If we're given a big, complicated task, sometimes instead of trying to solve it as a whole, it's better to first split it up into smaller subtasks, to solve all the pieces individually, and finally compose them back into a solution of our initial problem. In this talk, we'll be interested in compositionality in the context of finite state automata. And we will see that we can make some automata easier to handle by decomposing them into smaller pieces. So let's have a look at an example. Here you have a deterministic finite state automaton. By deterministic, we mean that for every state, for every input letter, there is a single transition starting from this state labeled by this input letter. We will only be interested in deterministic finite state automata. So from now on, I will just say automaton instead of deterministic finite state automaton. Remember that an automaton defines a language composed of the words that can be read starting from the initial state and ending in an accepting state. In this example, the language of our automaton is composed of the words that contain an even number of A's and an even number of B's. So this language can actually be defined as the intersection of the languages of these two automata. This one checks that the number of A's is even, and this one checks that the number of B's is even. This is the type of decomposition that we will be interested about. Note that in this precise example, the decomposition is not that impressive. We start with 4 states and we end up with 2 automata with 2 states. But let me just make the automata a bit more compact. If we now imagine that we generalize these languages in the following way. So instead of having just 2 letters A and B, we add more letters into our alphabet, but we still want to ensure that every letter appears an even number of times. If we still want to recognize this language with a single automaton, we will need an exponential number of states with respect to the size of the alphabet, because we need to keep track of the parity of every letter. On the other hand, if we're happy enough with an intersection, we only need to add a very basic automaton for every letter. Okay? So here we can see that by defining our language as an intersection, we can save quite a lot of space. This is what led to the following definition back in 2015. So we say that an automaton A is composite if its language is the intersection of languages of smaller automata. If the language of A cannot be decomposed in this way, we say that A is prime. Note that this mirrors the definition of composite and prime numbers. A number is prime if it cannot be decomposed as a product of smaller numbers. So we know that we can decide whether a number is prime or composite. What about automata? So this problem is shown to be decidable in this paper, where the authors define the following nice algorithm. So how do we decide if an automaton A is composite? So first, let me just state these 2 very basic properties of regular languages that are used by our algorithm. So regular language inclusion is decidable, and irregular languages are closed under intersection. So now, how do we define the algorithm? So we're given an automaton A. We start by listing all the automata smaller than A. So there are quite a lot of them. This n here is exponential in the size of A, but there are just finitely many, so we can list them. Then, second step, for every one of these automaton, we check whether its language contains the language of A. So if it does, that's good. If it does not, well, this automaton cannot be used as a decomposition of the language of A into an intersection of languages. So we just discard it. Okay? So all that is left is the automata that can actually be used in the decomposition of A. So what we do now is just we take the intersection of all of these languages and we check, we call this intersection the roof of A, and we check whether this is equal to the language of A. Note that we actually only need to check this inclusion. The reversed inclusion is guaranteed by step 2. Okay, now what? Well, if these two languages are equal, then A is composite because we have a decomposition right here. And if these two are not equal, then we claim that A is prime. Why is that? Well, remember, in step 2, we kept all the automata that could be used in a decomposition of A. So now, if we take any word W that is in this language, but not in this one, then we know for sure that for any decomposition we try to build using this automata, well, W will always be in there, and so we will never be able to construct exactly the language of A. Okay, so such a word is called a primality witness of A. Okay, so this is our algorithm. What's its complexity? Well, if we build explicitly the automaton that recognizes the roof of A, we need a doubly exponential space because we take the product of exponentially many automata. If we're a bit smarter and do this step, check the inclusion between the languages on the fly, we can get rid of one exponential for the price of some non-determinism. And then by applying Savage's theorem, we can get rid of the non-determinism. So all in all, this algorithm can be done in exponential space. Can we do better than this very basic algorithm? Well, we don't know. So a question that you might have at this point is the following. When we think about prime numbers, if we want to prove that a number is composite, we just guess a decomposition as a product of two numbers and check it. Why can't we do the same here? Why can't we just guess a decomposition of the language of A into two languages instead of having this exponential decomposition? Well, the problem is that things are not that easy when it comes to automata. So whereas a composite number is always decomposable as a product of two smaller numbers, sometimes more than two automata are needed to get a decomposition of a composite automata. Sometimes we need 3, 4, 5. There are families of automata that require arbitrarily many automata to get a decomposition. So we cannot simplify the algorithm in this way, unfortunately. So we don't know whether a better algorithm exists. Do we at least have some hardness result? Well, we have one. We know that the problem is n-log space hard. So yeah, the open complexity gap is still quite big between these two results, but nothing more is known yet. What was known prior to our work is that if we restrict the general setting to permutation automata, so a permutation automaton is an automaton whose transition monoid happens to be a group, then the problem can be solved in polynomial space. How does the proof works? Well, it works by studying the quotient of the automaton A. And so what we did was apply the tools developed for the study of permutation automata to unary automata. And by doing so, we were able to prove that in this new setting, the problem is actually solvable in logarithmic space. Okay? And so the rest of the talk will be devoted to the proof of this result. Before going further, let me just precise something. So here I said before that the problem is n-log space hard. Now I have a log space algorithm. How does that work? Well, we're cheating a little bit here. We're supposing that the automaton we were given is trim. That is, all the states are reachable from the initial state. If we have to trim the automaton by ourselves, then the complexity of our algorithm goes up to n-log space. Okay, let's go. So unary automata. What's a unary automaton? Well, it's just an automaton whose language is composed of a single letter, let's say A. Since all of the transitions are labeled by A, I will just erase them so that the figures look a bit cleaner. And so, yeah, the first thing you might notice is that since we have a single letter and we only consider deterministic automata, there is no branching. And so all of our unary automata will have this very basic lasso shape because, well, we start reading A's, so it's just a path. And at some point, since we only have finitely many states, one state will be repeated, and then we will be stuck in a loop forever. So yeah, every unary deterministic automaton has this very basic lasso shape. But this does not prevent them to have very interesting behaviors when it comes to primality. So for example, remember I told you before that in the general setting, some composite automata require more than 2 automata in their decomposition. So we proved that this is still the case in the unary setting. More precisely, we showed how to construct a family of composite unary automata such that for every one of them, if we want to get a decomposition, we need logarithmically many automata with respect to the number of states. So in particular, this means that if we take the whole family, we cannot bound the number of automata necessary to get a decomposition. So composite unary automata can still have interesting behaviors, and similarly, prime unary automata can also have interesting behaviors. So remember that we have this notion of primality witness, which is a word that can be used to prove that our automaton is prime. And we also showed how to construct a family of prime unary automata whose primality witnesses all have at least exponential size. So, okay, this kind of interesting and complicated behavior prevent us from just simplifying the basic algorithm in this setting. So in order to improve the complexity, we needed something more. What we did was study the notion of simply composite automata. So let's read the definition together. An automaton A is simply composite if it can be decomposed into its quotient automata. So what are quotient automata? Let me define that with some examples. So let's take a unary automaton A here. The language of A is the set of words whose length is a multiple of 6. And I define the quotients of A as follows. I start with an equivalence relation over the set of states that is consistent with the transition function. So here I have this equivalence relation. I have 3 equivalence classes, and they are consistent with the transition function. From a green state, I always go towards a blue state. From a blue state, I always go towards a purple state. And from a purple state, I always go towards a green state. So once I have such an equivalence relation, I can easily define a deterministic automaton by just taking the subset construction. So here, I have these 3 states automaton, green, blue, purple. And so this is what we call a quotient of A. The only tricky part is how to define the accepting states of the quotients. So remember, we want to decompose the language of A as an intersection of languages. So we want the language of A to be included into the language of its quotients. So we just say that, well, if the equivalence class has at least one accepting state, then the corresponding state is accepting, okay? So this one is accepting because there is one accepting state here, and both of these are rejecting. And so this is my first quotient. There is exactly one other non-trivial equivalence relation over this set of state that is consistent with the transition relation, and that is this one. So this time I only have 2 equivalence classes, the red and the orange, the state corresponding to the red one is accepting because I have at least one accepting state, and this one is rejecting. Okay, so these are my two quotient automata. And what I can notice is that the language of A is equal to the intersection of these two languages, because an integer is a multiple of 6 if and only if it is a multiple of 2 and a multiple of 3. Sorry, if it is a multiple of 3 and a multiple of 2. Yes, so the language of A is equal to the intersection of the language of its quotients, and so by definition, we have that A is simply composite. Okay? Let's take another example. We'll go a bit quicker. So we take the complement of the previous automaton. This time we accept all of the words whose length is not a multiple of 6. So if I take this equivalence relation, I end up with this quotient automaton. This time, all of the states are accepting because all of the classes contain at least one accepting state. And if I take this equivalence relation, oops, I end up with this quotient. Once again, all of the states are accepting. And so this time, the language of B is not equal to the intersection of the language of his quotients. Both of these quotients accept everything. So the intersection also is everything, and B is not. So we have that B is not simply composite. Why is this notion interesting? Well, we proved that in the unary setting, it's actually the same to be composite or simply composite. So one direction is trivial if an automaton is simply composite. In particular, it is composite. Why is the other direction true? Well, the very vague idea is as follows. If we have a composite automaton and we're given decomposition, we can transform every element of the decomposition into a quotient by folding it onto itself. And so this proves that the automaton is also simply composite. Okay, now that we have that, well, it's in order to decide whether an automaton is composite or prime, we can just decide whether it is simply composite or not. So for example, the automaton B here that is not simply composite is prime. And so in order to get the desired result, that is that we can decide if an automaton is composite in logarithmic space, it is enough to prove that we can decide if an automaton is simply composite in logarithmic space. How do we do that? Well, the whole idea is that we don't want to construct the quotient explicitly because this would require polynomial space. So instead of doing that, the important thing is, so we want to check whether the language of A is equal to the intersection of the languages of its quotient. So what we know is that the language of A is included into this intersection by definition of the quotient automata. So the only thing that remains to check is that whether the words rejected by A are rejected by his quotients. So for every rejecting state of A, we will check whether there exists one of the quotient that reject the corresponding word. Let's see that with an example. So if we start with this one, we start in a rejecting state, and we want to check the equivalence classes in which this state here is. So this one is not good because there is at least one accepting state, and so this state will become accepting when we go to the quotient. However, this one is nice because both of the states are rejecting, and so the corresponding quotient will reject all of the words that are rejected by this state. So for this state, we're all good. The words rejected by this one will be rejected by one of the quotients. Let's go to the next state. So if we look at this equivalence class, it's not good. There is one accepting state. And if we look at the other one, it's also not good. So this is actually bad because the words rejected by this state, for example, the word A, won't be rejected by the quotients. All of the quotients will accept the word A, And so this automaton, the language of this automaton won't be equal to the intersection of the language of the quotients. Therefore, this automaton is not simply composite by definition, and therefore, by the theorem, this automaton is not composite, hence it is prime. Okay? Let's have a look at the next one. So once again, we start with the first state. We look at the equivalence classes. This one is bad because we have accepting states. This one is good. We have only rejecting state. So we're good with this one. We go to the next one. This equivalence class is good, and we can use the same to guarantee that actually all of the words rejected by this automaton will be rejected by at least one of the quotient. As a consequence, the language of this automaton is equal to the intersection of the language of its quotients, and therefore the automaton is simply composite, and in particular it is composite. Okay? How is it log space? Well, actually we can represent the length of the cycle and the position. We can encode the length of the cycle and the position of the rejecting and accepting states in binary. And then we only have to check some modulos and things like that. And all of this can be done easily in logarithmic space. Okay, so that's it for our main result. The talk is coming to an end. Let me just remind you of our result. So our main result is that primality is decidable in logarithmic space for unary automata. As a consequence from our proofs, we get that every composite automaton has a decomposition of logarithmic width, and every prime automaton has a primality widthness of exponential size. And actually, both of these bounds are tied. We construct some families where the bounds are reached. So this is our results. What needs to be done? Well, obviously, the ultimate goal is to improve the complexity gap in the general setting. However, this is quite complicated. So, yeah, we cannot really use the same tools that we used here because, I mean, the equivalence between composite and simply composite automata for unary automata is necessary for in our proofs, and this is unfortunately not the case in general. There are some very basic examples of composite automata that are not simply composite. So yeah, maybe instead of considering the general setting, we should try and consider other specific classes. Maybe, yeah, we should try and determine for which classes this is true, and then this might be easier to get better results. Another interesting direction is the following. So we can consider the following variants of the primality problems. Here we define a composite automaton as an automaton whose language can be decomposed in an intersection of other languages. What if instead of only allowing intersection, we allow any type of Boolean combination? So then the primality problem should still be decidable. I mean, we can similarly as we did with the basic algorithm, list all the smaller automata and then try all the possible Boolean combination. There are only finitely many of them up to equivalence. And so this is decidable. This looks more complicated than the problem where we only allow intersections. So maybe it might be easier to get some hardness results here. I don't know. It might be interesting. So, okay, that's all for me. Thanks for your attention. I hope you enjoyed the talk. And so, yeah, if you have any question or interesting idea, please don't hesitate and contact me and my co-authors. So thanks for everything and see you.